Okay, all right. Well, happy Friday. End of week 3. Happy Friday. All right. Okay. Let's talk about the midterm. That's coming up Wednesday. It always seems like a good idea at the beginning of the quarter, and then week 4 comes and you go, oh, maybe I shouldn't have scheduled a week 4 midterm, but because it comes up way faster than you expect. But here it is. Okay. It's going to be pen and paper exam, so we'll just take it in the classroom. And again, I'll send out a seating chart. And if you're watching the video and you're like, I need to sit in a left-handed desk, send me a message, and then I'll make sure you get put into a left-handed desk. Otherwise, I'm just going to assign you to some location in the thing. I think most of these desks, even if they're left-handed, like they're still okay to write with your right hand, I think. But anyway, okay. And then definitely you'll need to bring a calculator, and then you will be allowed to have a sheet of notes. Okay, 1 sheet of notes, writing on the front and back. And you'll submit your sheet of notes when you turn in your exam. Okay, and I will also send out a seating chart. All right, so there will be 5 problems, and you have 50 minutes. So you got to budget your time wisely. And I'm trying to kind of figure out, exactly how much work each thing should be. So one will be kind of this vector-based calculus. We had a little example of this where, we had the OLS loss function in vector notation or vector form, and then we took the gradient with respect to W. And you'll have something similar to that. And so you just you take the gradient of something with respect to a vector. And when you do that, you want to make sure the dimensions line up correctly each time. So I strongly recommend that you write the dimensions of each matrix underneath, so that you can make sure the dimensions are correct. That should be a habit you get into, because if you just write the letters W and X, you're used to, in like regular old multiplication with scalars, you can just do W and X and the order doesn't matter. They're all like just 1 by 1 scalar values. But in matrices, you can't just multiply any X with any W. The X has to be, the dimensions of X need to align with the dimensions of W when you multiply them. Okay, well, anyway, so that's the first problem. Second one, we got gradient descent. I'll provide a function. It'll be two values coming in, 1 value going out. Okay, and I'll give you some kind of arbitrary starting point. I'll provide an arbitrary learning rate, and you will perform gradient descent. So you'll figure out the gradient at that starting point, and then you'll take a step in the opposite direction. So you have that. Okay, regularized loss. I'll give you a tiny little data set, maybe 3 points, 4 points, something like that. I'll give you a equation for the potential line of fit. And with that, you'll figure out what the OLS loss is, and then you'll figure out the lasso loss, you'll figure out the reg loss, and that's that. I think that one should be pretty quick. And then manual leave one out cross-validation. Again, tiny little data set, 3 or 4 observations. There will be like maybe 2 competing models, okay? And you'll perform leave one out cross-validation for each model. So, and when I do that, I'll tell you like, okay, here's the 4 data points, and when you leave the first one out and you fit this model to the remaining 3, this is the resulting, slope and interceptor. These are the resulting things, right? So you don't have to actually fit the things themselves, but what you're going to do is you're going to say, okay, well, if this is the model, if this is the slope and intercept, what do? You plug back in the point that was left out, and you get, its prediction, and you compare that to the actual value, and you'll start to calculate kind of this cross-validation error that way. Okay, and then a handful of conceptual questions. All right, and so the conceptual questions will cover up through, I guess, lecture 3-1. So, because on Wednesday we started neural network stuff, so none of the neural network stuff. Okay, so up to week 3, Monday, will be, I guess, fair game for the conceptual questions. Okay, I hope that makes sense. Any questions? Yeah.
Can we put anything on the note sheet?
You can put anything on the note sheet. I guess don't look up like past exams or something, and like don't put like past exam problems on the note sheet or something. But if you want to make up your own problems, you want to put homework stuff from the homework on the note sheet. That's fine. If you want to shrink down little pieces, shrink down the lecture notes down to little segments on your note sheet, that's also fine. Okay. Yeah.
Would that be coding questions on Excel?
No coding. Yeah. You get enough coding stuff in your homework. So. Okay, all right. Let's look at today's lecture then. What are we doing? Week 3, Friday. We left off. So I had introduced neural networks on Wednesday. And okay, quick review quiz. Hold on, let me also pull up my viewing quiz for Friday. Okay. All right. So let's see how much we remember. Okay. What's the dimensions of W1? Matrix W1. What are the dimensions of matrix W1? 2 by 3. All right. Two rows coming in because we got 2 nodes coming in, and then three nodes going out, so it's going to be 2 by 3. Okay, what about W2? 3 by 1. Okay, and then Y is n by 1, X is n by, well, in our case we got n by 2. Okay, there you go. Okay, and then so this is kind of where we left off on Wednesday, and we said, okay, we're going to do this forward propagation business, and we take our input matrix X, we multiply it by W, that gives us our Z values. We apply an activation function to our Z values, and that gives us our activated values, and then we multiply that by W2, and that's going to give us, I guess, our Z2 values, and then we apply an activation function there. So this is the dimensions of our weight matrices. W1 is 2 by 3, W2 is 3 by 1. We have this activation function. We're just using the sigmoid or the logistic function for it. But again, we can choose whatever we wanted to. And then again, this is kind of how the forward propagation works. X times W gives us Z, apply F to the Z, then we get A times W2 gives us our other Z, and we apply F to that Z, and we get the Y hats. Okay, and then we could do it with bias terms. I've left that for your next homework assignment. So we're going to do it without bias terms in the lecture notes, and then for your homework, you'll get to work with bias terms. What we are doing is we want to minimize the loss function. Okay, so I saw a question on CampusWire, which is like, how do we figure out what our weights are, or how do we figure out what the bias terms are? And it's we figure out the weights, with this goal in mind, minimizing the loss. Okay, so kind of like, for least squares regression, we could jump straight to the answer because it's already a solved problem. But one idea for least squares regression is you say, okay, well, we want to minimize the sum of squared residuals, and you can kind of adjust the knob for intercept and slope and kind of turn those until you get down to the minimum value. Okay, and similarly, now we have just a lot more knobs. We've got all 6 of these values in W1 to adjust, all 3 of these values in W2 to adjust. So we have 9 values that we can be adjusting here. And, you know, we're not going to adjust them ourselves manually. Okay, we're going to use the gradient descent algorithm to do it. But the gradient descent algorithm is driven by this loss function. And it's all in the idea of we want to minimize the loss. And the loss is calculated by taking the actual values in our data and we subtract off the predicted values in our data, right? And so if we can get the predicted values as close to the actual values as possible, this value is going to shrink something close to 0. You know, we square it and we're taking the mean squared error there. But that's what we're trying to do, okay? So in the next few slides, to deal with our gradient and stuff, we're going to be trying to figure out the gradient of our loss function. Now, we're going to use just a slight modification of the loss function. This is the mean squared error. And this is like the sum of squared error, but divided by 2. And we're just going to multiply the loss by a constant, which is n over 2. The value that minimizes j are the values of w that minimize j are going to be the same value of that minimize l. And it's just like when we replace 1 over n with 1 over 2, that just makes some of our constants kind of disappear. We don't have to worry about it. Okay, so that's what we're going to be doing. All right, so this process where we find the gradient of the loss function with respect to the different weights and stuff, this is, I guess, known as backpropagation. And, you know, there are algorithms for dealing with backpropagation in this kind of, for really big networks, because we're going to kind of take this manual analytic calculus approach. And, you know, when you have these really deep neural networks and stuff, you kind of just do it layer by layer rather than trying to do it all at once. So here we're kind of taking this analytic thing, but again, for deep learning, you just kind of go layer by layer rather than what we'll be doing. Let me go ahead and give you your first view quiz answer for today, which is the letter B. B as in bear. B is your first view quiz answer, B. Okay, so again, what are we trying to do? We're trying to train the network, and training the network means figuring out what our weights are. We have in our very simple model, so even as simple as it is, where we have, you know, two x nodes coming in, one y value going out, and 3 nodes in the hidden layer. So it's hard to think of something much simpler than that. Even with our very simple structure, we have 9 values to adjust. Okay, 6 values in W1, 3 values in W2 that we can adjust, right? And our training is figuring out what those weights should be. Okay, and so to minimize the loss function, we're going to use gradient descent. Again, a lot of these kind of iterative algorithms aren't guaranteed to find a global minimum. You know, one thing is our loss function is pretty simple. It's just sum of squares, so it's pretty simple. It's a convex loss function, so it will generally have okay performance. But you know, gradient descent depends on a gradient existing, and depending on your data, depending on your starting location, there could be areas where there is this really kind of big, almost flat region, right? And basically, you know, gradient descent is basically like rolling a ball down a hill, right? And so if you kind of start with a very kind of flat region, even if it's not perfectly flat, it might not roll, okay? So it can get stuck. And so sometimes you have to try different starting locations, and the hope is that, you know, even if you start in different starting locations, they all kind of end up at some place where the performance is good, okay? And even if they don't end up, so, you know, you start over here and you figure out, you know, this set of 9 values and you get good performance, all right? You can start over here and you might end up with a totally different set of 9 values, but this also performs just as well. And if this performs just as well as these ones, then maybe it doesn't matter, okay? You know, well, anyway, gradient descent, we got to figure out the gradient. So, you know, what is the gradient? that's like, okay, we got to figure out, what is basically the derivative or the gradient with respect to our weight matrix, okay? So if we look at our two weight matrices, our gradient is going to be basically the matrix of all the partial derivatives of each component, right? So the gradient with respect to W1 is the matrix, right? W1 is a 2 by 3 matrix, and so the gradient will be a 2 by 3 matrix, and each component is a partial derivative with respect to the first element, the second element, the third element, fourth, fifth, and sixth elements, okay? Same thing with the gradient with respect to W2. Gradient of our loss function with respect to W2 is just the matrix of all of these partial derivatives, okay? And then if we have bias values in kind of gathered in a bias matrix, then you would need to figure out the gradient with respect to those bias terms, okay? And again, that's coming up in the future in your next homework assignment. Okay, so we are going to work through this back propagation, and yeah, I will just kind of talk through each of these things, okay? So here we start with our loss function. Our loss function is j, which is just half of the sum of squared errors. So we start with y minus y hat, okay? And we're going to square that, take that difference, square it, okay? And we're going to say, okay, what is the gradient? We're going to start with the W2 term, the second weight matrix, because it's kind of closer to the output, right? So if you think of like going from x, it's closer to the end. So we're going to find, okay, what is the value of the loss function, the gradient with respect to the second weight matrix? Okay, so what do we do? Well, this is we're going to say the gradient of the sum. This is kind of the sum of the gradients here, okay? And then so when I say, okay, what is this with respect to W2? Okay, so remember W2 is a matrix, and we ask, okay, what values change with respect to W2? Like if I were to change W2, what values are affected? Okay, the y values are not. The y values are fixed. That's part of our data, right? So there's no gradient with respect to y sub n, okay? But the predicted values, y hat, those do change, okay? Like if I changed my slope or intercept, or in this case just the weights in our second weight matrix, our predictions, y hat will change. Okay, so this is just applying kind of calculus, right? So we got yn minus y hat over y hat n squared. So I take that 2, it comes down, and then it's going to cancel out with this 1/2. So basically, I'm going to have the sum of yn minus y hat, and then I have to apply chain rule. So I have a -1 in front. This is a negative sign, so I'm going to apply chain rule, and then the chain rule says, okay, now we need to figure out how y hat changes with respect to W2. Okay, so this is what we have. And how does y hat change with respect to W2? Okay, well, we can say, okay, well, what is y hat in at all, right? And so y hat is the result of, so going back to what's happening here is we have our z values, and then we apply an activation function to our z values there. So we ask, okay, how does y hat change with respect to W2? We can split that into, okay, how does y hat change with respect to the z value right before the activation function goes, and then we say, how does the z value z3 sub n change with respect to W2? Okay, so this is where we are right now. So we for each observation, we got to figure out, okay, what is the difference between the actual observation, our predicted value, how much did how does y hat change with respect to this observation Zn, and this observations, how does that change with respect to W2? So this is where we are right now. Okay, so y hat's the result of kind of passing this Zn3 value through the activation function. So if we just think about, okay, what is the relationship? Y hat is just f of zn of 3, and so the derivative of y hat with respect to zn3 is going to be f prime. Okay, so whatever our function is, we got f, and then we have f prime. That's what this thing is going to be. Okay, and if this is our activation function, then we can figure out what f prime is. Right. Is this okay? This is just taking the derivative of f prime, and these are just scalar values here, right? This is just a single value. Okay, so from quotient rule, f is u over v, right? So then you get f prime being u prime v minus uv prime over v squared. So if we do this, we'll let u as 1 and v is 1 plus e to the negative t. And then, this is what is this? Math 31 in A, okay? Something like that. It's just calculus. All right, so anyway, this is what we get, right? So this is our f prime. This is the derivative of the sigmoid function, and this is what we have here. Okay, so that's fine. For simplicity, I'm just going to leave it as f prime, but we can know internally it's this thing, okay? So all I'm going to do is this is where we left off. I'm going to replace the derivative of y hats of n with respect to zn3. I'm going to say that's going to be f prime of zn3, knowing that f prime is equal to this, following our derivative calculus rules. And so now we ask, okay, well, how does Zn change with respect to W2? All right, so this is a good spot where we ask, okay, how do we get Zn in the first place, right? So we said we're going to take our matrix. All right, so the full matrix, okay, we're taking our A matrix, the activated values in the hidden layer, okay, from the hidden layer, multiply it by our second weight matrix. Our second weight matrix basically combines the three nodes together, right? And so we have, A2 is n by 3, we multiply by W2, which is 3 by 1, and they basically kind of sum those three values together, and we get an n by 1 matrix for Z, okay? And right now we're just dealing with the nth observation. So just looking at that one observation, okay, we're going to have one row in our A matrix, right? So A sub n is one row in our A matrix. We've got just basically three values. And then our W2 matrix is still three values. And basically this is kind of like this inner product between these kind of two vectors here, right? And we get, the output is going to just be a single scalar value, after, linear combination of these values here. Okay, and so the question is, well, how does this single value, Zn3, or Z3n, change with respect to W2? Okay, so we apply kind of our derivative rules, right? And so, where did I put my derivative rules? Is that week 1? So we had this thing, right? So we have, if you have something times okay, so we basically have this. I don't have the transpose here, but basically I got a 1 by 3 times a 3 by 1, and we're going to take it with respect to the 3 by 1. So I'm going to be left with AN transpose here. Okay. All right, is that okay? So we're saying, how does this change with respect? So again, one thing to note is anytime you say, I'm going to take the kind of the gradient or the gradient with respect to a vector, the resulting thing has to have the same dimensions as W2. So if W2 is 3 by 1, the resulting gradient of this 1 by 1 with respect to W2 also has to be a 3 by 1. Okay, and so if we do it to this, we're going to get AN2. If I don't transpose it, this will be 1 by 3. So I need to transpose. So we're going to get 3 by 1 here. Okay, so this is our result here. And so here I'm going to replace this thing, the kind of this partial of Zn3 with respect to W2, and I get this, this is going to be right here, 3 by 1. Okay, so if we look at what we have so far, it's going to be the sum of, and we have n of these observations, but for each observation I'm taking the difference between the actual and the prediction, kind of the derivative of that value Zn, and then I'm multiplying it by this 3 by 1 matrix. Okay, so the result of this thing is a 3 by 1 matrix, and then I'm summing it up. I have n of these observations, right? So we're going to sum for, we get this for the first observation, and that's a 3 by 1 matrix. We do it again for the second observation, another 3 by 1 matrix. We do it for the third observation, so on and so forth, and we just add them all up, and the result is going to be a 3 by 1 matrix, right? Is that going to make sense? Okay, so I could leave it like this, but what would be nice is if I can get rid of this summation term. And when we do matrix multiplication, a lot of times there is kind of an implicit summation, right? So when you do matrix multiplication, and if you just take a vector and you multiply by another vector, even if just ones, right? Then suddenly, like you've got this long vector and you multiply by another vector of ones, then suddenly you're just adding them all up, okay? So what would happen if I just say, okay, well, you know what? All of these things have a subscript n, and what if I just replace them with their corresponding matrix, right? So, I've got n y values. What if I just replaced it with y, which is an n by 1 matrix, okay? What would happen, okay? Well, what happens is I get, this n by 1 thing, right? The y's become an n by 1. The z's become an n by 1. And then the a, okay, becomes a 3 by n matrix, okay? And if we do this, like, I can't multiply. I can't multiply n by 1 by a 3 by n and stuff like that. So we run into this a little bit of a kind of a roadblock here. But so what can we do? Well, we think about what are the values, each of the values being kind of multiplied here, okay? So we say, all right, well, you know what? When we're looking at the first observation, I'm going to take my first y value, subtract off my first y prediction, multiply it by my first z value here, okay? And then I'm going to multiply it by kind of the first row in here. And then for the second one, I'm going to take my second y value, second y observation, second value in z, and I'm going to multiply by kind of the second row in here, okay? Or actually, I guess when it's transposed, it's going to be first column and then the second column and third column, okay? So what I'm going to do is I'm going to bring this thing, okay, this an transpose, I can bring this to the front, okay? And we're still multiplying the same values here, okay, inside the summation, right? So I haven't messed with anything here. So, we're still multiplying all the same values. So the first value times the first value times the first value times kind of the first column of values, okay? And then if we go to the second value, second column of values, and now it's like second column of values, second value, or first column of values, first value, So I can kind of rearrange these scalar terms, and then now we can say, okay, well, now, so if these two things are equivalent, can I now just kind of expand them to the entire matrix? And now this thing works out a little bit more, okay? So here, if I expand all of A, rather than just having one column of 3 values, three rows, one column, okay? We're going to have 3 rows, n columns, okay? And that's going to multiply with the expanded y's, right? So the y's are going to be n by 1, okay? Now, how do I deal with these y's? This. When I expand this, I'm going to get an n by 1, and when I expand this, I'm going to get n by 1. What we actually want to do is we want to take, okay, the first element in, or I guess the first row, right? We're going to do the first element times the first element, and then the second y value times the second z value, the third y value times the third z value. So to handle that in matrix form, we're going to do element-wise multiplication. So this is just this is the symbol that I'm using for element-wise multiplication between matrix elements. Okay, so I've got this n by 1 times this n by 1, and this is just consists of multiplying, the first value in y with the first value in z, second value in y with the second value in z, third value in y with the third value in z, right? So this is the element-wise multiplication there, right? So the product of this and this is going to be n by 1, right? And if you follow the Welch Labs video, the author calls that delta 3, but it's just kind of this n by 1, this matrix, n rows, 1 column there. And then we can see, okay, if I multiply this by this, the resulting is going to be a 3 by 1. And that handles all of the summation, okay? Because when you do the 3 by n times the n by 1, you're doing each element, or each kind of, all n elements are getting multiplied, and then you're summing them all up, okay? Which is nice, right? So it's the same thing that we have going back here, where we're doing all n elements, okay, and then we're adding them all up, and we're able to get rid of the summation by using matrix multiplication. So, I could have done it just fine. I could have written a loop. I could have said calculate this out, run it n times for I and whatever 1 through n, and then sum them all up, right? But this is going to help us out. This is going to speed things up by, rather than having to run a loop that says do this multiplication and then sum them up, I can just say, just do matrix multiplication, and then when you do the matrix multiplication, it's going to take care of the summation there. Okay. So that was kind of a lot. Do we feel okay with how we got to this point? Great. Let me give you your second view quiz answer, the letter D. D as in dog. D as in dog. Okay, so now let's find the gradient with respect to the first weight matrix. Okay, so the first weight matrix is very similar. The beginning part starts off kind of the same. We say, all right, we've got n of these terms, and we're going to take each observation minus our prediction. We're going to square that, add them up for our loss. Okay, and we say, okay, well, how does it change with respect to W1? The only thing that changes with respect to W1 is Y hat. And then we say, okay, apply chain rule. How do, Y hat with respect to Z3 sub n. How does Z3 sub n change with respect to W1? So we start off the same way that we did when we were finding the gradient with respect to W2. Okay, this part, just a touch different, okay? So now we say, okay, well, how does Z3 sub n change with respect to W1? Okay, we go, oh, okay, well, Z3 sub n is the result of, taking your activated values, okay? And multiplying, we're gonna say, okay, well, how does it change with respect to the activated values, and then how did the activated values change with respect to W1, right? So we split this into this, okay, and then we say, okay, Z3 sub n is this is the product. Okay, how do we get Z3 sub n? So we took our activated values. So if we go, what slide is this? This is 26. So if we look back to our diagram, right? To get these values, we took our activated values and we multiplied it by our second weight matrix. Okay, where did the steps go, right? So we say, okay, where did these come from? These came from the A2 multiplied by the second weight matrix. So that's where we are now, okay? So we said, okay, this is taking our A2 matrix multiplied by our second weight matrix, okay? And so what is the what is the derivative or the gradient of z3 sub n with respect to an, okay? This is going to be W2, okay? W2 transpose. So here we get W2 transpose here. Okay. So we plug that in. And again, I'm keeping all of the dimensions underneath here, so we can kind of make sure everything is still kind of working. So this here is, so far, as a scalar. This is W2 transpose, which is going to be a 1/3. And then we say, okay, well, how did the activated values change with respect to W1? We go, okay, those activated values our A2 activated values is just the kind of that second, our hidden layer, those three values there. And we passed them through that sigmoid function, right? So we've got this sigmoid function here. So we've got another sigmoid function, right? And then we say, okay, well, in that hidden layer, we have three nodes. So when we look at, say, A2 sub n, this is, we've got three values here, right? We got a row of three values. So this is also just a row of three values. The nth observation is a row of three values here. Okay, so here I've got this, and this is a row of three values. And if we think about what's going on, we've got this 1/3 and this 1/3. We're doing element-wise multiplication, right? We're taking kind of, when we look at W2, okay, W2 is currently, it's a column of three values. And we do the first times the first, and the second times the second, and the third times the third. But right now we have it kind of transposed. So, but it's still, we want the first times the first, second times the second, and the third times the third. Okay. Okay, and then so we say, okay, well, how did the second values, okay, our z2 sub n, right? So we got kind of this row of three values here. How does that change with respect to W1? So this is like the weirdest part. So if we think about what is, this is the result of multiplying our input matrix X times the nth row in our input matrix X times our first weight matrix, okay? So if we think about what is X, in the nth row in X is, we've got two values, 1/2, and then we multiply it by W1, which is a 2/3, and the result is the nth row in our Z matrix, which is going to be 1/3, right? And our question is, how does this change, this 1/3 thing in the new up here, change with respect to W1, which is a 2/3, right? So we're saying, finding the derivative or the gradient of a 1/3 vector with respect to the changes in the 2/3 matrix, all right? So how does this work? Okay, well, if we kind of look at what's happening, right? Basically, I'm taking the nth row in our X matrix, which is these two observations, this 1/2, and then here's my W matrix, which is 2/3, and when I multiply that, I get this 1/3, right? And we can say, okay, well, how would this row change if I were to just like mess with this first value here? Okay, well, when I do that, it would, it gets xn1 times this, and this product, this quantity changes. How much? How much does it go up? It goes up by xn1. Okay, and if I change anything in this top row, okay, then basically it changes by xn1 times anything up there. Okay, if I change anything in the second row, it's going to change by a product of xn2. Right. So if you think of again, one way to think about the gradient or the derivative is you can say, okay, what if I add like this tiny little h to it, right? Tiny little perturbation, and figure out the numeric gradient, right? And so if I add any kind of epsilon value to any of the elements in the top row, then it's going to change by xn1 times the epsilon. If I change anything to the second row, it's going to change it by xn2 to the thing, right? And so what ends up happening is that when we take kind of the derivative of z2 sub n with respect to w1, it ends up being just a 2 by 1 matrix, the transpose of this thing. Okay, so and it almost kind of makes sense in this kind of way, right? So even though I'm getting a 1 by 3, which is a product of this 1 by 2 times a 2 by 3, when I say, okay, what is the gradient of this with respect to this, we're going to get basically this 1 by 2, but the transpose of it, a 2 by 1 matrix. So that's what we're going to have here. So if I bring this down and if I say, okay, how does z2 sub n change with respect to w1? And I say, okay, we're going to take our nth row in x and transpose it when we have this 2 by 1. Okay, we look at this and we go, oh, this thing doesn't multiply out at all. Okay, but again, if you keep track of each of the elements in each of these things, right? So this is just a 1 by 1 value, right? A scalar value. This is we have 3 values in W2 and 3 values in the nth row of Z, and we know those are being multiplied element-wise. Okay, so I can kind of do this element-wise stuff here between these two things to make sure these get multiplied. Right? And what's happening with this? Well, we have a 2 by 1, and basically we just want to make sure that we're going to do it to kind of the first element, okay, and then we also want the second element. So far this is all going to combine to a 1 by 3, and the result is we want a 2 by 3. Okay, we want a 2 by 3 matrix. So what I can actually do is I'm going to rearrange this. I'm going to bring this to the front, okay? So here I've got this 2 by 1 multiplied by all of this. All of this combines to a 1 by 3. And then if we keep track of our dimensions here, the result is going to be a 2 by 3, which is what I want. Yeah.
Well, what allows us just to switch the order however we want?
We're not switching however we want. We have an idea of what we need our final thing to be. Okay, so we say, all right, what is this J with respect to W1? W1 is a 2 by 3 matrix. So we know the final result has to be a 2 by 3 matrix. Okay, and then if we think about, okay, what are the elements being multiplied together, right? And again, so if we think about, what are the elements being multiplied together to produce, say, Zn here, we've got, these 3 values and these 3 values, kind of, the first and the first being multiplied by the second and the second and the third and the third. And so that's kind of what we're doing here. We're keeping track of each of the elements that are being multiplied. So this part we can do kind of the element-wise multiplication here. And then, and again, I can't multiply this with this, right? I got a 1 by 3 and a 2 by 1, and those things aren't going to combine. And we know that the result has to be a 2 by 3. So thinking about how did the elements get multiplied to form this, we end up bringing this to the front, and that's going to help produce the dimensions that we know we need to end up with, while also preserving the order of the multiplications. I know it feels very uncomfortable, the idea of kind of moving your matrix terms around and multiplying. And even this whole element-wise thing, this is not something that appears in regular linear algebra either. Okay, and so there is a little bit of kind of like what is going on with these things, and ultimately, perhaps we need to just treat everything as just single scalar values and just having these double, these nested loops and stuff to kind of calculate all of these quantities and bring them together. And the matrix multiplication is a little bit more of like a convenience thing. So this is not like strictly linear algebra. We're doing a few kind of wonky things that say, hey, you know what? The computer is able to do element-wise multiplication very quickly, and we can kind of take advantage of the fact that when you do matrix multiplication, summations take place. So, so maybe it's a little bit more like we're taking advantage of linear algebra structures to kind of speed up our computations, but perhaps internally we should treat these all as like individual scalar values that kind of get combined into these things here. But yeah, if we do this, we get this kind of 2x3 structure, which is great, okay? But again, this is just for the nth observation, right? So we have our nth observation in x, 2x1. We multiply it by, the nth observation in y, and the nth prediction of y, and the nth this and that. And we get a 2x3 structure, and that's for the nth observation. And then you'd say, okay, well, I would do this for the second observation, okay? And I would do this again for the third observation. Each observation is going to produce this 2x3 matrix. And then the resulting gradient is the sum of all of those kind of 2x3 matrices like on top of each other, right? So you can kind of imagine like almost like a stack of like cells or something, right? And you got a 2x3, you stack a 2x3, stack a 2x3, and then what's the summation of all of those things? That's going to be this entire thing. Can we get rid of the summation sign by kind of expanding our x from the nth observation in x to like the full x matrix? Can we do that? Okay, well, we can try, and we can just kind of see what happens. And so with the if I expand from the nth observation in x, okay, and to the full x matrix, this would become a 2 by n matrix, right? And I think about, okay, well, what happens with these things, right? All right, this becomes an n by 1 vector, right? And again, thinking about, all right, what are the elements all being multiplied here? I've got, this is going to become an n by 1 vector as well. And we say, oh yeah, you know what? We're doing element-wise multiplication here, right? And so this is the same term from earlier, where we had y minus y hat element-wise multiplied by f prime z3. So we can call that delta 3, but we can still have this thing. Okay, W2, there's no subscript n, so there's no expanding. It's just the same 1 by 3 matrix for all of this. Okay. And then when we expand this Z matrix, okay, Z matrix right now we have the nth row, which has 3 values in it, the nth row. So when I expand that, we're going to end up with an n by 3, okay? And we can say, okay, well, how am I multiplying all of these things, right? So these multiply out to an n by 3. And we can, and these will all kind of combine with this n by 3 element-wise. And so we have this entire thing is n by 3. We element-wise multiply it with this n by 3 matrix. And then we multiply that against our x matrix, which is 2 by n. And the result is going to be a 2 by 3. So I've further carried out the multiplication. This n by 1 multiplied by this 1 by 3, n by 3, this is n by 3. This entire product is n by 3. This is 2 by n. 2 by n times an n by 3 gives us a 2 by 3, right? So all of this here we'll call delta 2. That's, again, following the Welch Labs video there. So you should watch those Welch Lab videos if you haven't done so. They're pretty good, okay? And so we have, this is what our gradient of J with respect to W1 is. Okay, it was kind of a lot. Hopefully you can kind of work through this. And then the next part is, okay, so we've done all of this work. This was the hard part, this part. And then now we have to turn this all into code that our computer can work with, right? But coding it up is actually rather straightforward, and I'm out of time. But we'll take a look on Monday, and we'll code this up, and we'll run it. And but if you got the function like this, going from this function down to the code version, it's like, oh yeah, that looks exactly like that. Okay, and it kind of works out that way, right? So we'll take a look at that. Let me give you your last view quiz answer for today, which is the letter A. A as an apple. A as an apple. Okay, and so, this is kind of back propagation, and we, we work through this kind of in this calculus-based, finding the derivatives and the gradients. As it's a bit of work, and again, for a deep neural network, we wouldn't actually go through this. We just kind of go one layer by one layer, and we just say, okay, how did this second layer change with respect to the previous layer, and then we work backwards that way. But yeah, we'll call it a day here. Have a good weekend. We'll see you Monday.